Okay, welcome everyone once again. So this second session will be a theory on graph neural networks. The objective of this session is to develop a theoretical understanding of graph neural networks. What is its expressive power? What are the limitations? And what are the possible solutions or the direction towards possible solutions? So I'll start now with this session. Just for a recap, in the previous session, we dealt with how the underlying geometry of data is important towards the design of architectures. We generalized the convolution on graphs. We discussed several learning tasks on graphs and how they can be performed at node level, edge level, and graph level. And we also discussed graph transformer and the necessary recent improvements on this direction. So let's start with the outline of the presentation for this session. We'll discuss the graph isomorphism problem. It will be followed by the Weisfeller-Lehmann test, which is a test for graph isomorphism. Then we'll see how expressive power of GNNs can be quantified in terms of its capability to distinguish non-isomorphic graphs. It will be followed by the limitations of 1WL that leads rise to the higher order GNNs, and it will be followed by universal graph neural networks. What are the conditions for that? And finally, I'll discuss on the notion of or the use of different aggregation functions and their limitations, and also the bottlenecks of GNNs. So these all together will provide different concepts that are important towards the design of GNN architectures. And it also helps to understand different blind spots that are necessary to consider when we are developing GNN architectures. So let me start with the graph isomorphism problem. So if we consider this pair of graphs, this graph contains 6 nodes and also the second graph, and the corresponding adjacency metrics are at the right. So can you look at this pair of graphs and see? Yeah. So can you look on these two graphs and see if they're same or different? You see that the number one thing, the number of nodes are same in both of the graphs. The number of edges are same in both of the graphs. If they would be different, this would be different graph. I mean, the graph should not be the same. But since the number of nodes and the number of edges are same, the next thing we need to see if there is a one-to-one correspondence between the nodes that preserve the edges. So if it's the same, then we can say that these two graphs are isomorphic. So let me show you in the next slide. The two graphs actually are isomorphic to each other. It's just that it's plotted in a different fashion, but both of the graphs are same because there exists a one-to-one correspondence. For example, this 4 becomes the node 0 here in the next graph, and the colors represent the one-to-one correspondence. So the colors represent that the nodes are the corresponding nodes for are same in both of the graphs. And when we are doing this correspondence, we also see that the adjacencies are being preserved. So if you see the edge with the orange color and the green color, it's the same in the next graph, even though the indexing is different. So graph isomorphism, two graphs are isomorphic to each other if there exists a one-to-one correspondence between the nodes such that it preserves the node adjacencies, as we see from this example. And formally defining, two graphs are isomorphic if there exists a bijection between the vertex sets of the two graphs. The bijection means the one-to-one correspondence, such that any two vertices U and V are adjacent in G if and only if its correspondences are adjacent in the next graph. So for any particular edge in the first graph and second graph, you try to see and it's being preserved. If a node is being mapped to another index, then the corresponding edges is still being preserved. So this is the key definition. This is the main definition of whether two graphs are isomorphic or not. So we'll see why it's important. Before that, let's find out whether there exists any algorithm to find whether two graphs are non-isomorphic or isomorphic. So for this simple example, we could actually solve it or understand it visually, because it's a small graph and we can actually spend some time finding the correspondence like in the previous slide. So for a graph with a large number of nodes, it may not be possible to be determined. I mean, to determine this correspondence visually, and actually also in practice, we would require some algorithm that does this computation. So far, it's not known whether a polynomial time algorithm exists for this problem or if the problem is NP complete. However, this problem is of significant interest given its practical implications. For example, if we have this similar kind of algorithm, it could be able to detect symmetries of combinatorial objects. And also, if we have a database which stores graphs, for example, for molecules, if we don't have a way to determine if two graphs are isomorphic or not, we may end up storing the same representation. We may end up storing different representation for the same graph. So it's important to have an algorithm to detect such symmetries so that we can only represent a canonical representation of the graph in while storing in the database. So these are very useful practical implications of this problem. So even if this thing doesn't exist, there is present a classical heuristic to test if two graphs are not isomorphic, which is called the Weisfeller-Lehmann test. It is an old algorithm that was proposed by Boris Weisfeller and Lehmann in 1968. That is basically a iterative node culling algorithm, which leads to determine if two graphs are not isomorphic. So it just becomes a sufficient. It becomes a necessary condition that on a particular condition, it tells that two graphs are not isomorphic, but it cannot guarantee whether two graphs are isomorphic. But still, it's of useful importance because it has its equivalence to message passing based GNNs that was discussed in the previous session. So we'll see that how this is related to a GNN and how it helps to quantify how much expressive GNNs are and what are the failure conditions of a GNN model. So the WL test is a node coloring algorithm that is represented by this on the right. And at the core of this is this node coloring feature update. At the initially, it initializes the feature vectors of all the nodes in the two graphs in the similar way, and these are hashed into colors. And after that, it tries to iterate until a stability condition. It tries to see whether the multi-set of colors for the graph first and for the second graph, if they're dissimilar, then it returns that it's non-isomorphic. Otherwise, it keeps on repeating. And if a convergence condition is achieved, then it's not able to determine, and it says it may be possibly isomorphic. So this is how it works. We'll see in the next slide its demonstration. But what if we try to abstract the steps 3b and 3c, it can be written as such. There's a injective function, hash function, which considers the combination of a particular node and its neighbors' colors, and it uses this and passes to the function to output a node color for the node I for the next iteration. So this is the main abstraction of the steps 3b and 3c. In 3b and 3c, it's being done for both the graphs, but otherwise this is the same thing that is happening. And it's injective, meaning that for a unique combination of Ci and Cj, it must output a different mapping for every distinct combination. And this final color representation, the multiset, it becomes a color histogram that is compared to determine if two graphs are not isomorphic. If they are different, then they are not isomorphic. So let's run this 1WL algorithm on this pair of examples. We saw that visually, there exists a one-to-one correspondence between these two graphs, and they're essentially the same graph. They are isomorphic to each other, but we'll try to run with this test. So the what it does is, like we saw in the previous slide, it takes in the color of a node and its neighbors and maps by using an injective hash function to output the node. So let's see in these two graphs how many distinct combinations of Ci and Cjs are possible. There are actually three. First, this corner, this node which has single neighbor, it's represented by this at the third. Then we have a node which has three neighbors. This node, one neighbor, second neighbor, and third neighbor, which is the second hash function and being computed here. And third, there are three nodes which have two neighbors each. This node, two neighbors. This node also has two neighbors, and this node also has two neighbors. So there are three possible combinations of colors, and hence we can get three distinct color outputs as a result, and correspondingly, the colors of the nodes are updated in the next iteration. So it happens, this step is iterated till a step where we have a stable node coloring. The colors don't change. So this is the first step. Now we'll again repeat the same process to output colors for the next iteration. So let's see now. We have for the previous iteration, we had three distinct combinations. Now we have five distinct combinations. So for example, this green node has three yellow neighbors, which is represented by this. This orange node has one yellow neighbor, which is represented by this, and so on for all the different five combinations. So because there are five different combinations, we output five different colors for corresponding nodes, and they are updated in this step. So each of the node has now a different color for this iteration. Again, we repeat. Again, we have, for example, this purple node has a gray and two light colors like this, which is represented by this third line. And similarly, if we have all the combinations, so the black node here has a gray neighbor, which is denoted by this last line. So we still have five different combinations of Ci and Cjs, which is the node color and the node neighbor colors. So we get five different colors once again, and we repeat this step again. We'll still have five different colors. That means the colors are not changing now. So now this becomes the stopping condition, and at this step, whatever the color histogram of colors we have, it will be used to determine if these two graphs are not isomorphic or possibly isomorphic. So we see that there is one instances each of the first four colors and two instances of the red color in this iteration. It is the same for both the graphs. So hence the final output is that the color histograms are the same for both the graphs. Because of this test outputs that these two graphs may be possibly isomorphic. It doesn't guarantee that these two are isomorphic graphs, although we know for fact that these are isomorphic graphs. Hence, this WL test becomes just a necessary condition. It's not sufficient to guarantee whether two graphs are isomorphic. It's just if, for example, if these color histograms would be different, if, for example, this node would have a different color as opposed to this node, which would result in different color histograms, then this algorithm could output that these two graphs are not isomorphic. But right now, since these both are same, it outputs possibly isomorphic. So this is how this WL test works, and it can be used to determine if two graphs are not isomorphic. So the WL test can be used to determine the expressive power of graph neural networks. We'll see how. So it was shown in these two works by Keoli Xu and his co-authors and Christopher Morris and his co-authors that the expressive power of GNNs are bounded. The expressive power of GNNs that are based on message passing are bounded in the expressive power. They're not universal, it means. And this expressive power can be measured in terms of the graph isomorphism. As such, these GNNs are at most powerful as the 1WL. So we have this condition where the message passing GNNs expressivity is either less than or equal to the 1WL. So we'll see how these two are related and why is this condition present. So if you see in both of the equations, the 1WL update equation for the color of the node and the feature update equation for the feature update of a node in message passing based GNNs, we see that it has a message aggregation from the one hop neighbors, and similar also happens in the message passing GNNs. So hence the operation being done is the same in both the cases, but there's a difference of the function f. So if the function f, if you see in the 1WL, it becomes an injective hash function, because for each different combination of the CI and the multiset of CJ, it gave a different color output. So in message passing GNNs, we don't know the nature of f so far. We know that it's a function which consists of parameter and aggregation. So we don't know whether it's injective or not. If it would be injective, then it would be of the similar nature of 1WL, and we would have an equal expressivity. But since we don't know of f, what is the nature of the f function, then its expressivity may also be lesser than that of 1WL. Hence, the GNNs are at most powerful as 1WL. And this is a visual representation of the message passing thing, because when these colors are updated for the next layer, also the message passing GNNs also performs the feature update in a similar fashion. So this is the equivalence of GNNs, and because of this equivalence, we can quantify how much GNNs are expressive or how much they are powerful in terms of 1WL. So because the 1WL was an upper bound, can we make an architecture which is equal to 1WL, like the expressive power of the message passing based GNNs is equal to 1WL? Yes, we can make it. We need to take care of the function of f. So in the previous slide, I told the nature of f is unknown in message passing GNNs. So that's why we didn't have a equality. We had a less than equal to bound. So now if we focus on this f and we make it injective, because in 1WL, the function provides distinct color for distinct color and the neighbor color pairs. So if we make the f injective in the message passing GNNs, then we have a GNN that is the most powerful GNN compared to the 1WL, and its expressivity becomes equal to that of 1WL. So a model was actually developed by this paper, which is called graph isomorphism network. In this case, they focus on this aspect of the message passing GNNs, and they make sure the function that they have is injective. And as a result, it becomes a 1WL equivalent GNN. So what is graph isomorphism networks? So it's of the similar form as a message passing GNN, where its equation is represented by this, and it focuses on two things. One, the G aggregation, and the G function here and also at this point, and the sum aggregation. So the G function must be injective because of the fact that we want f as a result to be injective. So the G function is approximated using an MLP, and there are two G's in this part, and there's only one MLP which is used to approximate G. So it's natural because MLPs can compose different functions as well. So it can be used by only one MLP, and then we have this condition satisfied to have a G injective function. Second important thing is the sum aggregator. So sum aggregator is necessary because if we use, for example, to understand, different aggregation functions are important to consider when we are dealing with discrete features. So in this case, if you consider yellow node is a node which is receiving information from the red and the blue nodes, and these are the two graphs. If you use max function, these two graphs would have the same output, because in this case, if we consider max function, it fails to distinguish the neighborhood messages in these two graphs. Although we know that in the second case, the yellow node has two red neighbors. So if we do a max, element-wise max, it would simply be 1 because the red has 0 and 0, 0, 1. So it will take the max of the neighbors, and it will have the same output in the case of max, and hence it fails to distinguish that these two graphs are different where in terms of the number of neighbors of red color. Similarly, in the second example, we have again the two graphs where yellow is the node that receives messages. And in this case, the max fails as well. And also the average operation fails. Average neighborhood aggregation also fails to distinguish, because the average of a blue and the average of a two blue is the same. The average of one red and the average of two red will also be the same. So it fails to distinguish that they're actually different more neighbors in the second case. So what if we did sum? If we did sum, then we would simply be able to count that there is only one blue neighbor here, whereas there are twice the number of blue neighbors and twice the number of red neighbors here. So in both these cases, sum is able to distinguish, and it's also it counts that in an injective fashion. And to make this function f injective, we must consider this G as MLP and the aggregation as sum. And then we have there's another term which is epsilon, that is a scalar added to that. It requires this term as well. So then if we consider these three key ingredients, then we have a construction of this form, and this results, this is named as graph isomorphism network, because its expressive power is as the same as 1WL test that of graph isomorphism. Yeah, I have a question. How are we enforcing the MLP to injective? I mean, yeah, it's based on the universal approximation theorem, because it can learn any function, and the function that we want to learn here is an injective function. And element-wise multiplication, yes, I mean it applies to each of the different feature elements, the same MLP. Or maybe you can think in such a way, it's a feature. If MLP has 3 layers with one hidden layer, then it outputs a d-dimension feature by taking an input d-dimension feature vector. So the MLP is being applied in a similar fashion. So if whatever this feature vector would be present, this will be a feature vector, like a d-dimensional feature vector. So on this MLP is applied. So this is the natural way. So don't get confused that this part is using a flattened feature vector of the graph structure. It's not, because under this, the computation explicitly considers the graph structure, because for each node, it's only considering the neighbor information and not all the node information. So this MLP is different from what MLP was used when I discussed about the permutation invariance of GNNs in the previous session. So this MLP, the use of this MLP is only that this function would be a injective function. If we remove G, you would see that in the GCN, in the graph convolution, this G was just a W matrix, the weight matrix. But simply using one weight matrix doesn't satisfy the universal approximation condition of MLPs. So hence we need at least one hidden layer to satisfy that condition. So this is why the MLP is used here. And the next injectivity condition is satisfied by the sum aggregator. And we saw why, because the mean and max aggregator can fail at different conditions. And finally, when we perform any graph level classification, in the final layer also, the injective function should be sum. So this is the global pooling. It's also called the graph readout function in GNNs. So when we are trying to pass the final layer node information to the to represent one graph vector, we also use the sum aggregator here. So these are all the necessary conditions, and then we have a message passing based GNN model that is as equivalent as the 1WL in terms of the expressive power. So it means that whatever the graphs that is able to be distinguished by 1WL will also apply to message passing GNN, which is the GIN, because now we have a similar model as the 1WL. And let me say that I'm using one, I just used one here. In the previous slides, when I was doing a demonstration of WL, there was no one, but now I'm using one because this one represents that I'm just coloring one node at a time at every iteration. I mean, it's simply node coloring step, one node coloring step. That's why it's called 1WL. And why it's called 1WL, we'll see later that there are also KWL, which does node tuple coloring, which is of the size K node tuple. So let's see, before that, let's see what are the limitations of 1WL. So 1WL failed to distinguish simple non-isomorphic graph. If we see these two examples, this example of the pair of graphs of decalene and bicyclopentyl. These are molecules. So these are two different graphs because if you see the blue node here, it is connected to a red node, and on that red node, another blue node on this side is not connected. So which is part of the cycle of this blue. So if you see these two blue nodes on the right, it's connected to single red node, but it's not on the case of the left graph. So, I mean, if we look at this kind of global information, we know that these two graphs are different and they're non-isomorphic. But when we run the 1WL algorithm, that the demonstration that I showed earlier, if we run step by step on these two graphs, we'll find that after the convergence condition, we'll have these color histograms where there are 2 colors of red, 4 colors of blue, and 4 colors of yellow. It's the same as on the right. And this is a failure condition. The 1WL is not being able to distinguish that these two graphs are different. So when we have any message passing based GNNs or any graph isomorphism network, consider any number of layers, 100 layers, 50 layers, or 10 layers, or 2 layers. It will, or any possible combination of weight, train on any matrices. It cannot predict the differences between these two architecture, because theoretically now we know that based on the 1WL condition, it always supplies the same feature vector output for both of the neighbors. And why it is so? Because by definition, 1WL and also message passing GNNs, it fails to consider any higher order graph information. So visually, we see that these two are different when we are looking in a global perspective. But if 1WL and message passing GNNs, they are only focused on aggregating the local information. So when they're aggregating the local information, this red node has 2 blue nodes. This red node also has 2 blue nodes. But we see that in this case, this red node has 2 blue nodes of the same cycle. But in this case, the red node is connected to blue node of different cycles. So this is some sort of a global information that we are looking visually. But when 1WL is considering the local information, it's not taking into account this global structure from the graph. And because 1WL fails to distinguish these two graphs, message passing GNNs also inherit these limitations. And because of the equivalence, it also cannot distinguish these two graphs. And whatever the number of layers, like I said earlier, whatever the number of layers you use to train, it will always give the same feature output for decalene and bicyclopentyl because of this construction. At the same time, the 1WL test also fails to count patterns such as cycles and triangles. And we can assume, we can imagine like detecting patterns such as cycles and triangles in graphs are very important for the applications that we do in real-time graph analytics. For example, if you see the transportation case of Google Maps, if there would be a cycle, the map would never suggest you a route to cycle a particular road. If you're going from one location to another location, you would never want a route which performs a cycle, right? So if a model is not being able to detect any cycle, it means the model would perform very catastrophically in trying to predict routes for a passenger or routes for any user that is using Google Maps. So this is one of the conditions. So slowly, like when we discuss these kind of things, we come to understand why the theoretical understanding of the models, where it fails, where it doesn't fail, is important to properly understand how these models can be deployed in real world conditions. So the failure to detect cycle is one example which would perform which would provide a very serious limitation when we are trying to develop any models for transportation maps. So, and similarly, like in this case, this is a pair of circular skip link graphs where each node in both of the graphs have 4 neighbors, 2 adjacent and 2 with a skip. So the skip length in the left graph is 2 because 0 is connected to another node with 2 hop distance, whereas on the right, 0 is connected to another node with a 3 hop distance, like 1, 2, and 3. So it's connected to the third node. So this is the difference, and that is the skip link of the graph. So these two graphs are also different, but 1WL will always fail to distinguish these two graphs, and the color histograms would be the same in both the cases. This is because 1WL considers only one hop neighbors. Each of the nodes have 4 neighbors, and there's no any distance information present, like what is the hop that is being connected. So So basically, these are the limitations of 1WL. And because of these limitations, it gives rise to a new class of architectures, which are called higher order GNNs. So before going into the GNNs part, let's first see the WL part. We see that in 1WL, it colors nodes. So this coloring of a node V and U are basically nodes from the node sets of both the graphs, and these colors are updated at each iteration. So this 1WL can be extended to KWL to perform coloring of K tuple of nodes. So if there is if you consider K number of nodes and consider it as one unit, if we have an algorithm for coloring this K tuple of units at once, then it becomes a K dimensional WL algorithm, where now the V and U represents a K tuple of nodes rather than just a one tuple of nodes. That's why the WL algorithm that was at the base as a basic that was presented earlier is referred as the one dimensional or one WL algorithm. And now we can have a generalization up to a K tuple. So because looking at, for example, this example, we were able to look visually. It's different because we're looking at multiple tuple as single unit. So if we look this three nodes as a single unit and this three as a single unit, we see that these two graphs are different, but coloring singly one node at a time did not reveal the differences. But now with when we try to look that in three tuple or four tuple, then we know that we have a distinct difference, and it moves towards incorporating a more higher order structure information. So this is the main difference, and hence the coloring of the node tuple is performed finally instead of the single node. So the key things to note here in relation to 1WL and KWL is 1WL is as powerful as 2WL, because when we are coloring one node and when we are coloring two node, the coloring of two node would still have one hop neighbors only. So they become equivalent. And for all K greater than equals to 2, the K plus 1 WL is strictly more powerful than KWL. It means that if we consider, for example, 3WL and 4WL, then there must exist, or there actually exists certain graphs which are not being distinguished by the 4WL or 3WL, and they're actually being distinguished by a higher 5WL or 4WL. So I mean, you get the idea. The K plus 1 WL is strictly more powerful than KWL. It means that there are certain class of graphs on which the higher WL is more successful, and on which the lower WL is fails on distinguishing those kind of graphs. So this is a very useful insight, and naturally you can think that we know certain things. We know that 1WL fails on simple graphs, but we also know that if we have consideration of K tuple coloring, then we have more powerful nodes because of this result. So this insight is used to construct strictly powerful higher order GNNs, which focuses on node tuple coloring. Sorry. So now let's see example of this in practice. So how for example 3WL and 4WL, what is the differences? So this is a pair of graphs. On the left there are two disconnected components. On the right there is this graph of 8 nodes. So these two graphs are distinguishable by 3WL when node coloring of 3 tuple of nodes is considered. But if you consider this very complex, complex looking graph, it's not very complex, but look, looks messy. So anyways, this is an example where actually the 3WL also fails, but the higher order would not fail. So if you consider 3 tuple of node coloring in this part, then it's able to distinguish these two graphs, but in this it's not being able to do. So this shows the justification of this insight and its usefulness, that we can have more powerful algorithms or more powerful isomorphism tests by considering more higher number of tuples coloring as one units. So this is basically the higher order WL test. Now these are used to develop higher order WL GNNs. So this is like inspired by the KWL, KGNNs were proposed, which are as expressive as the KWL test, and it becomes strictly more powerful. But these architectures have now O n to the power k complexity. Because in message passing GNNs or 1WL, we are just focusing on single node coloring. The complexity was ON, or again, the number of edges. But in this case, we are considering the coloring of k node tuples, then it becomes n to the power k. So if you're thinking that now let's move ahead and create a model which is as powerful as possible. So if you do that, it requires the tensors to be, this sized, and also the complexity of this order makes the models intractable in practice. So, for example, if you would require if you would need a 3WL, it would require n cube. If you see the example from the previous slide, so on this, even 3WL fails. So if you want 4W or 5WL, it will require complexity of n to the power 4 or n to the power 5. So this becomes intractable. So in the work by Maron and his collaborators, they actually improved the complexity of cubic to have quadratic complexity for a model that is as powerful as 3WL. So this is an improvement in such a way that now they have 3WL equivalence without having n cube representation. So this is an improvement, as only second order tensors are required. However, this 3WL GNN, the architecture which is shown here, it still has the cubic speed complexity, because the way how it is able to achieve this 3WL equivalence is the multiplication of two dense order matrices, which are MLP outputs of at this step. So because of this matrix multiplication step, which is being done using this, which is basically done after the output of two three-dimensional matrices, it becomes this matrix multiplication step results in cubic speed complexity. So this is how we are proceeding one step at a time. Like in this case, we saw that we can have actually better powerful model, but that comes at the cost of very intractable computational complexity. Now in 3WL GNN, which is represented by this architecture, it solves, it tries to improve the limitation, bringing to n square. But this n square is still more compared to the message passing GNNs or 1WL, which only had the ON complexity. And this pipeline represents the computation that was used for 3WL GNN. Now we don't have the sparse graphs. We have the node information, edge information, and the graph structure represented in a 3D tensor. And these are, because of these operations, the matrices are densified and we lose the sparsity. So this is the reason why we require quadratic and cubic memory and speed complexity. So this, it's better than the n to the power k, but still it's very difficult to scale on medium or large scale graph data sets. So there's actually a great deal of research that is being done on this side, and how to still achieve higher order graph neural networks, but trying to take care of the complexity. So I will not focus on all of these details, but I just wanted to show how this is one of the directions with which we can create more powerful GNNs and get rid of the limitations of having simple 1WL equivalent models. So now we move to a condition, determining a condition in how GNNs can be made universal. So till the previous few slides, we saw that the expressivity power of a GNN was always related to the 1WL, 2WL, 3WL, or KWL. But let's try to look at the expressivity of a GNN from a different perspective. So an equivalence of 1WL was based on the case that nodes were anonymous. So when we performed 1WL, remember that at the input, we considered each of the node color same for all of the nodes. So there is no any discriminating features. So only because of this assumption, it became 1WL equivalent, because the initialization of all the node colors would be the same at the input. Now, in a work by Andrea Lucas, he proposed that, or he derived certain conditions under which GNNs can be made Turing universal. And when they are Turing universal, it actually solves the graph isomorphism problem, because it's a more stronger condition than the graph isomorphism expressivity. So GNNs, the same message passing GNNs which has the linear ON complexity and represented by this, can be made Turing universal under three conditions. The first condition is the GNN layer must have powerful message and update functions. By powerful message and update function, it means that it must be able to approximate any class of function that is represented by a graph. So to achieve this function f and at this aggregation f, simply MLPs can be used with at least one hidden layer to represent this universal approximation. So this is how we achieve the first condition. And GN is one example, for instance. In the second condition that is necessary, the network should have sufficient depth and width. By depth of the network, we mean the number of layers, and by width of the network, we mean the feature vector dimension at each of the layer. So collectively, the depth and width of the model is referred to as model capacity, which I will discuss later in the following slide. But the network, to have this Turing universal, with the first condition, the second condition, it must have sufficient depth and width for the problem that is being tackled. And the third and very important condition is that each node in the given graph must have unique or discriminative features. So it comes to a condition that initially we know that the nodes are anonymous, but if by somehow we can pre-compute certain information so that each node has some discriminating node features, then with the presence of this condition and the previous two, the second and the first condition, such a GNN could be Turing universal, and it's a strong condition than as compared to the graph isomorphism expressivity. So this is a theoretical result. Now let's see how it's practically achieved. So for the first condition, like I told, using MLPs at these two steps is enough. For the second, we need to take care of the depth and width, which for the bounds, which I'll tell in the next slide. And for the third, it's the most challenging step. So by definition or by availability, we don't have each node that has unique node features. If you consider, for example, a molecule which has 5 nodes, there can be 2 nodes which are carbon, 2 nodes which are oxygen, and so on, 1 node which is nitrogen. So there are actually multiple nodes which have the same atom, so correspondingly the same features. So it's very hard to have availability of unique or discriminative feature. At the same time, if we forget about the atoms and all, if we simply consider the node ordering, it's not very straightforward because any possible node ordering can be considered, and we have to consider all n factorial examples if we are trying to use node index as a unique features. Yes, if we use node indexing, they become unique, but because of this limitation that we have to consider all n factorial possible ordering, this is also not a solution to be considered. So then this leads to a research direction of positional encoding for GNNs. So this Laplacian eigenvector is one example, and there's also several other works that are recently being done. So the idea is to have a pre-computation based on some adjacency matrix count or substructure count and assign as node features so that it leads to unique features, and then some of these conditions can be justified to have a very powerful model. So there's a great deal of work for positional encoding for GNNs. I will not focus everything in detail. The Laplacian eigenvectors that was discussed in the previous session is one of the example, and some of the examples were in the positional encoding that was used for the fully connected transformer GNNs. So these are the theoretical bases on which the design of GNNs are help. So like I told, the depth and width are collectively called as model capacity, and just writing a network has sufficient depth, should have sufficient depth and width is may bring a question like what depth to consider or what width to consider. So naturally, the same paper by Lucas, he derives certain conditions, certain bounds for this model capacity. And if D is the depth and W is denoted by the W denotes the width, then DW the multiplication of DW denotes the model capacity. And it shows that like for all these different kind of classical problems related to graphs, different bounds can be derived. And each of these are dependent. The model capacity is dependent on the number of nodes in the graph. So for example, for the shortest path, the D and root over W must be of the order of this, at least root n by log n, in order to have a sufficient number of depth and width for the model. So this is one of the interesting results that was derived in this paper. The details of this, it's not possible for this lecture, but like you can refer to this paper for like what GNNs can and cannot learn, and the discussion and derivations on depth and width. And also there's a very good blog respective to the paper, which is easily accessible and where all these different things are discussed. So the important thing to note here is that the modal capacity would always correspond to the number of nodes in the graph. So as a general rule of thumb, like you can imagine, if you're dealing with a problem where the node sizes are very large for a graph, you should definitely have a DW, which is proportional to that. And if you have a smaller graph, which has maybe 10 or 20 nodes as compared to the earlier one, then you should have a smaller modal capacity. So this is proportional to the number of nodes in the graph. So this is an important thing to note. And also the trade-off. So all these bounds are a multiplication of depth and width. So it's also one of the important things to note here. Now we're coming towards the discussion on aggregation function. So this continues the discussion that we had earlier, that sum is an injective function and the condition at which mean and max aggregation functions fail. So let's see even the failure condition of the sum. We'll see that. So on these three different architectures, which are very popular, all of these popular GNN architectures use only single aggregation functions. For example, mean, sum, or in other architectures, max. So the use of single aggregator may lead to failure of distinguishing neighbor messages. And how this failure arises, we can understand by this demonstration, which was in a paper by Gabriel Corso and his co-authors. So let's consider the counting of messages, the continuous messages. So each node has a number, so 2, 0, 4, 1, and so on. And there are two graphs. So these two graphs essentially the same, but only the feature of the nodes are different. And V is the receiving message. So in this case, you see that V is receiving two messages with values 2 and 2. In the graph 2 case, the structure is the same, but the node V is receiving two messages with the values 0 and 4. So on this case, the aggregator that can fail is the average aggregator or mean aggregator, because you see 2 plus 2 by 2 equals to 2 and 4 plus 0 by 2 equals to 2. So the mean aggregator essentially produces the same output, but we know for fact that the messages are different, and it provides a different nature of information in both the two graphs. But if we take minimum or maximum or standard deviation of these two incoming messages, it would all help to distinguish these two graphs from each other, because the minimum of this is 2, whereas the minimum of this is 0. And similarly, the maximum is 4, the maximum is 2. So now we have two distinct outputs if we consider the minimum, maximum, and also by computation, the standard deviation aggregation function. So on this case, the mean or average fails. In the second example, which has 3 neighbors with 0, 2, 2, and 2, 0, 0, the aggregators that fail are mean, maximum, and standard deviation. But what succeeds is the averaging. So if you average 2 plus 2 plus 0 by 3 and 2 plus 0 plus 0 by 3, we'll have 4 by 3 and 2 by 3 for the two different cases. So the mean aggregator, the average aggregator that failed on the previous case actually succeeds on this case, whereas all the other aggregators that succeeded on previous case fails on this case. So this shows how the use of single aggregator may lead to failure of distinguishing different neighbor messages. And also these examples are also of the similar nature you can observe. So naturally one could think of how to solve this issue, how to go beyond using a single aggregator. The solution would be to use a combination of aggregators. And this was proposed in this model, which is called principal neighborhood aggregation. So in this case, this is the main equation. It's the same form of the message passing GNN that we saw with GCN, with GIN, graph isomorphism networks, and so on. So it's of the same form, but the only change that they have is this aggregation is no longer just the sum or any other single aggregator. Now it's a combination of 4 different aggregators: the mean, the standard deviation, the maximum, and the minimum. And they're also followed by some scaling operation. Scaling operation means, like, if a node has 10 neighbors and if another node has 100 neighbors, so the degrees help to scale this information to one range. So now this becomes the principal aggregator, which is replaced here. Rest everything is the same, similar as the GIN or GCN. So this is one solution to counter the limitations of using a single aggregator function. Like we saw in the previous example, the use of single aggregators may not be enough for different situations. And if for one situation, a particular aggregation function succeeds, it may not succeed for other situations. So the solution is to have a combination of these aggregators and help improve the expressivity power of the PNA. So this is a very important point to note whenever you are trying to implement any GNN model in future. Now, towards the final aspect, we'll discuss about some limitations of GNNs when we're trying to go towards deeper. So as a background, let's again recap the message passing. So if we're trying to have feature representation at one layer, second layer, so this slide will show like how the computational graph looks like. So for node A is connected to B, C, and D. So at the first layer, if the node feature of A is being updated, it will consider information from B, C, and D and updates the feature of node A. Similarly, at the first layer itself, the node B will take the feature from A and C because B is connected to A and C, and so on for the node C and D. So at the first layer, it just takes in the information from the one-hop neighbors. But when we go and do for the second layer, this A will again do the one-hop information only. But now that this B and C and D are already updated by taking their own one-hop neighbors, now when the node feature update of A is being done at the second layer, it will effectively contain information from the second hop. So this is how this computational graph gives the idea that at each L number of layers, information from L hops are being propagated to a destination node. So we encounter one phenomenon called smoothing. It's related to the way the GCN has this Laplacian smoothing operation. So recall that the GCN had this D inverse minus A and D inverse half HL and WL. That this is basically this is in the matrix form, which where the output becomes for all the nodes the feature dimension. So this is a form of Laplacian smoothing, and while it is a very important key characteristic of the GCN, because it makes the feature of nodes in the similar cluster as similar because of this smoothing, and it helps in the case of homophilic settings. Homophilic means homophilic setting means if there's a graph and nodes which are connected have the similar representation or the similar nature, then that's a homophilic setting of graphs. So smoothing is a useful feature there. But if we go deeper, if we have multiple layers of GCN, this smoothing may result to over smoothing and the embedding may become indistinguishable. We see this with this example. So these are the node embeddings plotted after 1-layer GCN, 2-layer GCN, 3-layer GCN, up to 5-layer GCN in the paper by Lee and his co-authors from 2018. So you can see that if there's one layer, the node embeddings are mostly distinct, mapped in this 2D space. But as we move from 2-layer, 3-layer, 4-layer, we see that gradually they are being converged to the same subspace. And if we have more number of layers, we would find that they're not being distinguishable. They're all being converged to the same space. This is happening because of this, the way the information is being propagated, and because of the smoothing, it's all of the embeddings are being assigned a similar value, or it's being assigned to the value which belongs to a same subspace. So this is a serious limitation, because if we actually want our certain node embeddings to be different, it would represent in a problem where we are not able to distinguish, and the performance of the GCN would be very poor. So what would be a solution for this? I've not mentioned the solution here, but like the direction is that if we try to incorporate some global graph structure into the model, then we can actually move towards improving this phenomenon, and we have better results. So for that, like there exists a great line of research. You can, if you're interested, you can see. But like the purpose of this slide is to just show that just applying GCN for an increased number of layers may result in oversmoothing, and it creates a problem because the node embeddings resulted may be indistinguishable and converge to a same subspace. Another limitation that arises when we are trying to build deep graph convolution neural networks is the information over squashing and bottleneck. So let me first introduce what are long range tasks. So consider this example. If for example, the feature of node A, if we want to predict something for the node this denoted by this red color, and we know for fact that it needs some information from the green node, which is at 4 hop, 1 hop, 2 hop, 3 hop, and 4 hop from the red node. If we know that the feature of this is necessary to predict some information for the red node, it becomes a long range task. I mean, this still looks like a short range because there are only 4 hops, but consider this would be a big graph and the hop would be at a large distance, 10 hop, 20 hop, or 50 hop. Then those kind of tasks are long range tasks because, I mean, basically in these cases, information is important from distant nodes which are not directly connected to a node. So this becomes a long range task. So naturally, to think of this in perspective of this computational graph, you can think that if we want to propagate something from a long range, we can have the number of layers similar to the number of this graph diameter. But if we have this deep several number of GNN layers, the receptive field of the node grows exponentially because it would have to consider it will have to consider the information from all different nodes from 1 hop, 2 hop up to k hop, and this leads to the condition where an exponential amount of information is required to be squashed into a single vector. So if this picture from the paper by Alon and his co-authors, this exactly shows this phenomenon that if information is coming from a distant, all these feature vectors are being summed or aggregated, or any kind of function is being done, but the end output is being squashed into one single vector, and there may be some critical information that can be lost. For example, the feature information from this 4th hop along with several other information reaches this node after L number of layers, for example 4 layers in this case. Then there may be a probability that a critical information from this neighbor may not reach there and get lost in this over squashing. So it consequently, this phenomenon may not be able to allow the model to fit properly on the training data. And we know for fact that, I mean, I think it's intuitive looking at this examples that, I mean, this is a small graph, but if we have large graphs, we would, because of this exponential increase in the receptive field size, it would be difficult to propagate information that is very critical to the distance, to the target node. So what can be a solution? A solution can be, if you think of this graph, why the problem arises at the first place? Because in the long range tasks, we want information from certain nodes which are not directly connected to the target node. So in this case, the red and green are not directly connected. But what if you connect this? Then it would become a 1 hop neighbor, and the information could propagate in just the first layer itself. So this is the solution. The solution is after performing a L number of GNN layers, you could simply perform a full connection at a final layer. So in final layer, we have a fully connected graph where a node is connected to each other node in this graph. So this will help to propagate information that would have gotten lost during this process in the over squashing. So note that this is just performed at the final layer. If we perform fully connected graph at each layer, then we may lose the graph structure information, the sparse structure information that we have in the graph. and that's actually very useful. We may lose that, but just having this at the final year provides a remedy for this problem of over squashing, and it allows critical information in long range tasks to reach to the destination node. So this is one example, and actually this is also very interesting research area. There may be some other methods that will be developed in the coming months or years for this. And because using a fully connected graph always presents a challenge. If there is maybe 500,000 nodes in one graph, constructing a 500,000 cross 500,000 matrix is very difficult in the RAM or the GPU's memories that we have for today. You can try yourself, like just creating a random tensors of 500,000 cross 500,000. So, I mean, whenever we are using a fully connected graph, we always have this computational challenges. So it's one way to do that. And the reason was that because there's no link that initially avoided this propagation of long range information, just make that link shorter. It becomes a one hop neighbor now. So then that's one way, but it's still a very interesting area of research. So we move towards the conclusion now for this session. I hope we developed a theoretical understanding of several aspects of GNNs. And why it's important, because this understanding leads to identifying several blind spots for a model for which, if we are pre-informed, remedies can be developed. And this expressivity power for the case of GNNs that are based on message passing can be quantified in terms of its ability to distinguish non-isomorphic graphs. And if we want to get improvement on this, we need to consider higher order structure information. But yeah, there are challenges when we are trying to have the higher order GNS that uses dense tensors. And finally, we discussed phenomena such as smoothing and over squashing, which may lead to critical and serious limitations. And especially for long range graph learning tasks, it is critical to account for such factors. So that concludes this presentation. I think this was short, and if you have any questions, we can discuss. I have left some useful resources on this topic, on understanding the expressivity power and what are the different limitations, how there can be solutions developed. And in the later couple of lectures in the evening by Christian and Fabrizio, you will see that you could find all these concepts useful to understand the papers that they will present in the later afternoon in the last two sessions. Because the architectures that develop are very powerful, and they kind of are solutions to some of the limitations that we discussed in this session. So yeah, thank you very much. I can take questions now.